my lighting might be really bad because it's it's night, so I can't rely. Usually I like the sun lighting look better. Sorry about that. We're gonna talk about electric potential energy. I'm gonna go over pages 17 and 18 in your AP Physics 2 packet. And yeah, we're just gonna talk about basically some of this is gonna be AP Physics 1 review, especially this page 17. So so the first question asks, write some energy equations that you could find to solve the speed at point B. This is just conservation of energy. Energy is never created or destroyed, so the initial UG, so E initial equals E final. Your initial, what was I going to say? Your initial energy is going to be UG, and then your final energy is going to be K mgh 1 half mv squared. You can solve from there. Now let's say you want to find the energy from B to C. Now H is equal to 0, so what that means is, yeah, there's no UG at the end. Now you have two options. You can do negative UG. Negative UG actually kind of works here. And basically you can say E initial equals E final, right? So UGA equals KB. The kinetic energy at B is going to equal negative UG plus K final. So KB initial, KB final. Now you're saying, wait, what the heck? Negative UG? It's because you're kind of like in gravitational debt. That's kind of confusing though. So what you could just do is just say, well, hey, I want UG here. If this negative UG stuff made no sense, no worries. You could just say K plus UG, right? So you can say there's UG here. Even though we said there's no UG here, you could say it. If you're mathematically inclined, you probably noticed that, well, you can just add U. Like when I had a negative UG here, that you can just add it. So, whatever way makes sense for you. Now so UG, a local UG, I like to call it, is equal to mgh, right? When your gravitational field strength is constant, but when you're in space, it's not going to always be constant. So what is the equation for UG in space? We use UG, this is the next question, UG equals negative G m1 m2 over r. And what this suggests is that if you're at an infinite distance away, you have no UG. So UG is equal to 0 at R is going to equal, well, it's going to be 0 joules when you're an infinite distance away. So as you get closer and closer, you lose UG, right? Because it gets more negative. Same thing going on here, right? When you get lower down to the ground, you're losing UG. So both equations are consistent. Now, this is what Einstein proposed that gravity basically was. It's just the warping of space-time. I honestly don't love I don't love the demo spandex with the mass on it. 'Cause it's like, yeah, but you're using gravity to explain gravity, but whatever. It's the bending of space-time. Also, space-time is like a 4D thing, and that sheet is spandex 2D. Here's how you can visualize it, though. And so at this point right here is when you have 0 UG. At that point, very far away, you're not under the influence, you're basically not under the influence of gravity because you're an infinite distance away. Maybe right here is going to be negative 10,000 joules, right? As you get closer, you're losing potential energy, and right here is going to be negative 20,000 joules. So that's when you're really close to the planet, you're getting a lot less, right? A bigger negative number, that means less potential energy. Let's move on to, and number 5, explain in terms of potential energy why a planet moves closer. Well, because of conservation of energy, as you lose potential energy, you're going to gain kinetic energy. And you're going to gain kinetic energy, right, or you're going to gain velocity in the direction of whatever you're moving towards. So as you lose UG, you gain kinetic energy to compensate, but guess what? Now you're losing even more potential energy because you got closer. So it's just this constant, conservation of energy. In order for energy to be conserved, you lose UG, gain kinetic, the total stays the same. Let's talk about now electric potential energy. How does this relate to electrical potential energy? So the next page is a little simulation. Hopefully you try the simulation, because, I don't know, I guess it was important to do. So you had 3 scenarios. You had a positive real close to a positive, you had a negative, or a positive real close to a negative, and you have a positive and a negative quite far away. What's the energy looking like in each of these states? And why? Well, when you have two positives right next to each other, you know there's going to be a repulsive force between them. Like charges, I don't know why I say opposite. Like charges repel. I don't know why I did this either. Repel, right? They want to get away as far as possible. So you know that force is going to be really strong. As soon as you let go, it's not going to explode, but it's going to go really, really fast. It's going to be gaining a lot of kinetic energy. Wait, you're gaining a lot of kinetic energy. You must have a lot of kinetic energy. Or sorry, wait, what am I saying? You gain a lot of kinetic energy. You must have lost a lot of potential energy, aka there was more potential energy here. High potential energy. Now we're going to talk about like electric potential energy, and I'll maybe make them separate. I have videos actually with the AP Physics C stuff. This is really physics too, but once you start learning more, I'll make videos. Okay, positive and negative. If they're really close next to each other, they're going to be repulsive. But when you let go, sorry about the noise, they're just going to move close. They're going to be just moving together. They're not going to move a whole lot. They're not going to gain a lot of speed. So we would say this is low potential energy, right? Right, this is low potential energy. Now, definitely low compared to this scenario where they're really far away, but they're going to gain, they have a lot of distance, a lot of space to gain a lot of kinetic energy. We would say this is higher potential energy. I'm saying higher potential, I really mean potential energy, and we're going to learn potential is kind of a different thing. So I'm going to say higher potential energy. Okay. Sorry about that. My brother thinks he's a real clown for that. So we're going to talk about this graph now, and we're going to talk about what the graph means and what that kind of does for us in terms of like giving us information. So we have a graph. This is the electric force versus distance of a proton that's fixed in place, and then a proton that's able to move around. So two protons. And then the curve looks like this. Question pretty bluntly asks, what is the area under the force versus distance curve? And if you remember from AP Physics 1, that was the work done by that force, because work is equal to force times distance times cosine theta, whatever. Force times distance. So the area would end up being the work done. Now, why does this make sense? Well, when you're really, really close, when you have protons that are really, really close away, they have a really high repulsive force, at least according to this graph, right? We'll learn exactly how to figure out those forces. Really, really high force. And that first meter, right, the work done is going to be like the force times distance. Now, we don't have a constant force. This force sharply decreases. But in that first meter, there's a really high force. There's a really high work being done. Contrast that to this meter right here, right? We're just looking at this area, right? And I'm going to kind of draw in just so we know. If we're looking at this area, the force is really low and they're far away. So in that same amount of distance traveled, there's much less work being done because there's a lower force. So the area is indeed force or work done. Now look up the equation for potential energy stored between 2 point charges. Write it down below. So if you looked it up, you would get that U E. So the electric potential energy between 2 point charges is equal to some number K, Q1, Q2, over R. This is very similar to our UG equation. It's actually kind of crazy how similar it is. Now, K, so Q1, Q2 are your 2 point charges, R is the distance between them. But what is K? Well, K is a cool constant. Just like, I don't know why I said cool. Didn't mean for that alliteration there. But it's a constant just like the gravitational constant, and this number ends up being equal to 9 times 10 to the ninth, and you can, do an experiment and figure that out, that yes, it actually does equal that. But what are the units for this thing? Well, we know that if we multiply two charges, the units are going to be Coulomb squared, right? So if I do 2 point charges, multiply it, that's Coulomb squared over meter. So whatever my units is has to take these 2 units and turn it into joules. So it's going to equal, well, joules, and then meters over coulombs squared. So it's like, okay, this cancels when you multiply coulomb squared with this, coulombs get canceled. When you divide this by meters, the meter cancels. You're left with just joules. And that's just that's like, I think it's called dimensional analysis, where you're trying to analyze, like, what the units would kind of be. Don't get too freaked out if that didn't make sense to you. That's just the units. This is on your College Board equation sheet, and yeah, life's good. Hopefully that made